All right, good afternoon, everyone. So let's start. So let's continue with the uninformative priors we discussed from the last Thursday. So we first introduced the philosophy of Bayesian model, right? So the biggest difference between the frequentist point of view and Bayesian guys is that, suppose in general, if you want to estimate some of the parameters from data, right? So the frequentist will, okay, these parameters are truly existent constant values, right? We don't know that. We know the value is hiding somewhere. There's not any randomness associated with that parameter. So to estimate that parameter or to find that parameter, frequentist came out a lot of ideas, right? They do a lot of random experiments and then they come out some estimator, right? For example, you take the average, like you toss a coin for, suppose your random experiment is to toss a coin. You want to estimate the chance you see it head up, right? There's a probability. We don't know the probability. And the frequentist will this probability as some kind of ground truth value, right? Hidden ground truth value. No one knows, right? How to estimate that probability. We can do 100 random experiments. We toss the coin for 100 times to look at the outcome of each random experiment. Like for example, 59 heads up and 41 tails up, right? So we can use that observation to construct estimator. Right? So that's the key idea. So the frequentist use the random experiments outcome to construct some estimator to approximate or to estimate the function value. So the randomness comes from the outcomes of the random experiments. Right? If you will, you toss a coin, right? This is a random experiments. The outcome itself is a random variable, right? If I collect observations, a bunch of random variables, I can construct a function. Over these random variables, we use that function of the random variables observations to estimate the unknown parameters. So the randomness only comes from this estimator or function of the random variables observations. Right? So if you want to quantify the uncertainty of your estimator, well, you need to assume some distribution about your estimator. Like that's where all kinds of hypothesis testing based on. Right? So this is frequentist point of view, but from Bayesian point of view, everything is random, right? Including the unknown model parameters. Right? For a truly Bayesian person, they will okay, every random variable, no matter you can observe its value or not, it is some random variable. So the core-tossing experiment from a Bayesian point of view will be considered as a hierarchical sampling procedure. We're gonna first sample this probability P from some prior distribution. Maybe it's from beta distribution or not. Right? And given the sample probability, then you generate the outcome. Like suppose your sample probability is 0.6, right? Then given 0.6, well, you do your tossing coin experiment, you see a bunch of heads up and tails up. And then we can imagine that Bayesian people will construct a joint distribution over the unknown model parameters and the observations of the random variables, right? And then we want to estimate these parameters. How can we do that? We just calculate the posterior distribution, right? Given a bunch of experimental results, right? We denote by theta d, right? What is the posterior distribution of the unknown parameters? Right? So the uncertainty is naturally summarized in the posterior distributions. Right? So we discussed the pros and the constraints, pros and cons about this point of view. But for Bayesian people, they found this really elegant and principled framework, right? But that incurs some criticism. Right? The criticism comes from like frequentist point of view, like, okay, now that you incorporate prior over the model parameters, you're doing some subjective you're introducing some subjective beliefs over those model parameters, which is not objective, right? If you're doing science, we know that science must be objective, right? Must be neutral. But you shouldn't incorporate some strong bias toward these unknown model parameters. So then there comes a problem, right? In the Bayesian framework, do we have a way to pursue objectiveness? Namely, we want to reduce the information content in the prior as much as possible. So this branch of Bayesian statistics is called objective Bayesian. This is just to address the criticism about that. Okay, you put strong prior over those unknown model parameters, you're putting some subjective beliefs. Right? So the objective Bayesian people are thinking of constructing priors which have as little influence as possible on the posterior distribution. Right? If we can find such kind of prior, this prior is called uninformative prior. Right? In other words, we want to make the prior so little informative such that we can let the data fully speak for themselves. This is the idea of uninformative priors. Right? This is particularly useful when you don't have any knowledge or don't have any strong preferences over some unknown latent variables, unknown model parameters, and you want your data to speak for itself. At the same time, you want to use this principled Bayesian framework to estimate posterior distribution rather than construct all kinds of estimators. So, as we discussed in the last lecture, right, the very first or the most intuitive uninformative prior will be the uniform distribution. Right? So we don't, in the uniform distribution, we assume, okay, the unknown model parameter or the latent random variable has the equal chance to take any possible values. Right? So for finite states, meaning that if it's a discrete random variables, it can take a finite number of values. The uniform distribution is 1 over k. K is the all possible values it can take, right? And for finite interval, it's just the probability density is just 1 over b minus a, which is just the length of the interval, which the range which the random variable can take the value from, right? Of course, if it is in a 2-dimensional, 3-dimensional space, as long as it's bounded domain, well, you can construct a similar probability density. But for unbounded domains, right, like if a random variable can take any possible value in the real space, so we are not able to construct a valid uniform distribution, right? Because for valid distribution, you need to ensure that the integral of the probability density over the whole domain is 1, right? But for unbounded domain, you cannot do that, right? So, but for pragmatic purpose, we're going to still use this prior, uninformative prior, which would indicate that this prior is proportional to constant. As long as you just plug in this into a drawn probability, you can still calculate a valid posterior distribution. That's fine. This is totally from pragmatic view, or practical point of view. And in this case, we call this uninformative prior or uniform prior as an improper prior. Improper, but practical useful. So these are about uniform distribution, a very commonly used and very intuitive uninformative prior, but uniform distribution is not always the best one for us to use. Why? There's one problem of the uniform distribution is that it is not translation invariant. So what does it mean for that? Well, as we discussed in the last lecture, right? If you pick any random variable lambda, right, we assign an improper uniform prior of that. That means P of lambda is proportional to constant. Now, if we make a little bit transformation over lambda, right? Like I define a transform random variable eta equals to square root of lambda, for example. In other words, lambda equals to eta squared, right? And then what is the probability density for eta? Ideally, we want the distribution over eta is also proportional to the constant, right? Meaning that if lambda is uninformative, then any of its transformation should be uninformative as well, right? Now, fortunately, if we apply the formula we discussed before, right? What's the probability density after the variable transformation? You'll find that the density of eta is proportional to eta. This is also improper, but anyway, after transformation, the prior is no longer uninformative. So how to address that problem? At the end of last lecture, we first talked about several special cases of the translation invariance. Let us consider the first instance, which is called shift invariance. Right? So suppose your likelihood has such kind of form, right? Given your latent random variable lambda or latent model parameter lambda, right? The likelihood of your observed value x has this form. It's some likelihood function of difference between x and lambda. So if your likelihood takes this form, then we say this likelihood is a shift invariant. What does it mean? It just means, okay, the likelihood value is only determined by the difference, relative difference between x and lambda. It doesn't depend on the absolute location of x and lambda, right? If you just move both x and lambda by a position of c can be whatever, right? And the likelihood value doesn't change at all. So this is called a shift invariance, right? And if we want to construct a uninformative prior, so we want this prior to be as consistent as possible with the likelihood. Why? Because if your prior kind of drastically different from the likelihood, you can imagine your posterior is kind of a integral, is kind of combination of your prior and likelihood, right? There can be a fierce battle between each other, right? So if you can make your prior to be as consistent as possible with the likelihood, like shift invariance in this particular case, you can imagine it will have much less influence on the posterior. Right? So the problem becomes, how can we choose a prior that also obeys the shift invariance? Right? So we can consider a general case where for arbitrary integral a and b, right? So we know that when it shifted, if it wants to obey the shift invariance, then we shift the interval by c, right? Which goes to a plus c and b plus c. They should have the same probability. Right? So that means you have to pick up a prior probability of lambda, a prior density of lambda, which satisfies this equation for arbitrary a and b and c. Right? So we have shown that last lecture. We just quickly go through that. If you do some simple integral variable transformation, you see that P of lambda will be proportional constant, meaning that if you choose P of lambda to be some uniform distribution, it will satisfy the shift the shift invariance, right? So contrast, we use the Gaussian likelihood as the example, right? Especially the Gaussian mean, right? If you assume the variance is fixed, right? If you just look at the Gaussian mean as the unknown random variable, right? This form actually satisfies the shift invariance form, right? So we found that if you want to put a prior which also shift invariant, you have to assign a uniform distribution over this Gaussian mean, right? By contrast, if you want to assign conjugate prior to this Gaussian likelihood, it must be another Gaussian. So you can see the difference. Right? Uninformed prior actually is totally different from conjugate prior. But there's some kind of like connection. If you take the variance of the conjugate prior goes to infinity, while your conjugate prior converges to the uninformed prior. That's what we have discussed in the last lecture, right? And then let us look at another type of translation invariance, which is called skew inverse. What is skew inverse? If your likelihood takes the form of this, so 1 over sigma and some function, some likelihood function of x over sigma, where sigma is positive, it's just some positive, and sigma is your latent random variable or your model parameter, right? Then we call this likelihood x space the skew inverse. Why? Because the likelihood is only determined by the ratio of x and the random variable sigma. Right? So if you multiply both x and the latent random variable sigma by a constant c, by applying the random variables transformation and calculate density, you'll find that the likelihood doesn't change at all. So I will highly recommend you to verify this by yourself. Just apply the formula we used. You'll see that point. So now we want to construct a prior over sigma, right, which also obeys the skew inverse. What kind of prior should we use? So again, the motivation is to let our prior to be as consistent with the likelihood as possible, so that the prior won't have too much influence on the posterior distribution. So to construct a skew invariant prior, right? Similarly, right? This is kind of similar strategy. We consider an arbitrary interval A and B, right? The prior should assign equal mass over an arbitrary skew interval A over C and B over C. Right? Then it will exhibit the skew invariance. That means for any A and B, and also positive constant C, right? So this, you must choose P of sigma, which satisfy this equation. Again, just apply the integral variable transformation, right? If you define a third integral variable sigma bar, which equals C times sigma, and you know, when C takes when sigma take A over C, then sigma bar will take A, and when sigma takes B over C, then sigma bar will take B, right? And then you just replace sigma in terms of sigma bar, right? Of course, for this derivative, you need to do some like transformation. So finally, you will end up with this, right? So the integral of A and B, P of sigma, will equal to the integral of P of 1 over C sigma 1 over C. So if you just set C equals to sigma, you will get the general form P of sigma, which is proportional to 1 over sigma. So now we can see that we derive a second form of the uninformed prior, which satisfies the skew inverse. All these mathematics are quite straightforward, so I won't show the details. But I highly recommend you to derive those yourself. It's just some practice of calculus. Okay.
I don't really understand why you need scale invariant or shift invariant in the first place. Like, what is the significance of those?
Okay, so the goal is to construct uninformed priors. So uninformed does not mean no informed priors. Actually, it's not possible in the Bayesian world. We want to construct such a prior so that when computing the posterior distribution, its effect on the posterior distribution is as little as possible. Right? So how can we achieve that? So imagine that, okay, this is your prior, this is your likelihood. Right? So if the prior is drastically different from the likelihood in every aspect, then when you calculate posterior distribution, remember the posterior distribution is just a combination of them and do the normalization, right? So you can imagine there can be a fierce battle between them. That means the posterior distribution will be strongly influenced by the prior as well. So to avoid this, right, we want your prior to be as less influential as possible, as little influential as possible on the posterior. So one strategy is, okay, I want to construct my prior to be similar or to resemble the likelihood in terms of some properties. Like, for example, this likelihood is a skew invariant. Okay, I will let my prior to be skew invariant, so that when I calculate posterior distribution, because they are kind of like similar, right? So you won't stop letting the likelihood to construct a posterior or dominant posterior computation, right? Otherwise, you can imagine like, okay, my likelihood is skew invariant, but my prior is not skew invariant at all. So you can imagine that the posterior won't be skew invariant, right? It could be quite far away from the likelihood itself. That's not what we want.
Depends on the problem, you will have some likelihood, you want to construct it.
Yes.
So any problem that requires
Yeah.
based on that.
Yes. Yeah.
So it's like problem by problem. Different.
Yes. This is quite different from non-objective Bayesian. Like for other Bayesian approach, okay, we're gonna first talk about prior, right? How to encode our prior beliefs or knowledge in terms of prior distribution. And the given data, I consider the likelihood. It's kind of rarely, unless for some computational reason, we rarely consider, okay, what's the connection between the prior and likelihood. But for objective Bayesian, for particular likelihood, we want to find a prior which gives the minimum influence on the posterior. So it's kind of likelihood dependent, or in other words, problem dependent. Okay. Any other question? Oh, it's not always the same form, but it's just to give you to reduce the influence from the prior. But mathematically, it doesn't guarantee that you're gonna give the same form as the likelihood of prior. If they give the same form as the prior, it's called conjugate prior. But if it's giving same form of likelihood, I don't know what is that called. But the key idea will be that, okay, I want to reduce the influence of the prior as much as possible in calculating the posterior. Okay. So again, we're going to use one detailed instance, right? So we use this Gaussian likelihood again, right? But now we just assume mu is fixed. Right? The mean is known and fixed, and we want to find some prior over this standard deviation sigma, right? So we know that the likelihood form takes this 1 over sigma and some exponential form minus x subtracted by mu over sigma squared, right? So they satisfy the skew invariance. Right? It's just the general form we mentioned. We mentioned this, right? So naturally, if we want to construct an uninformed prior for the standard deviation sigma, it's just proportional to 1 over sigma, because this uninformity prior will also obey the skew invariance, right? And remember, when we talk about the conjugate prior, right? With respect to the Gaussian distribution, right? We used to look at the inverse variance. Right? So from this uninformed prior, right? If we make some transformation over sigma, we know that the precision or inverse variance is 1 over sigma squared. If you do this random variable transformation, you calculate density, it will have the same form. It will have your uniformity prior over the precision proportional 1 over the precision. Right? Now, if you look at the conjugate part of eta, right? We know it's gamma distribution. Right? It has this form. It's lambda to the power of a minus 1, e to the power of b lambda. We can see that they're in general very different. Mm-hmm. This one? No, if you just calculate just 1 over a lambda. You just I mean you can apply the formula here. P lambda will be proportional to 1 over square root of lambda, and you need to calculate d sigma over d lambda. So if you just multiply into it, it will give you this 1 over lambda. Okay. The connection will be made if we set the parameters of the conjugate part both to be 0, which is invalid for a gamma distribution. Okay. But anyway, you can see the connection difference, right? So usually the uninformative part is very different from the conjugate part. Okay, so now let us look at a more general case. Okay. So we see that if your likelihood exhibits shift invariance, we just construct the uniform prior, right? Improper uniform prior. If your likelihood is a skew invariant, you construct the 1 over sigma squared, 1 over sigma or 1 over lambda, whatever, another prior, right? But what if your likelihood exhibits kind of any of other type of translation invariance, right? It is neither the skew invariance nor the shift invariance, right? Can we construct the prior which satisfies such kind of translation invariant? Or in other words, for any type of translation invariance, can we construct a general form of uniformity prior which is invariant under that translation? Okay. Such a prior is called the Jeffreys prior. Okay. So here is the definition of Jeffreys prior. So theta is assumed to be our latent random variable, right, or model parameter, whatever, right? So the Jeffreys prior is really also improper prior. It's just proportional to the square root of the Fisher information of theta. So what's the definition of Fisher information? I will give you a very brief definition in our previous lectures, but here we give a more detailed definition. So the Fisher information is defined as follows. So here is your likelihood. You take the second order derivative of your log likelihood with respect to theta. Then you take the expectation of this likelihood under the distribution of x given theta. And then you take minus sign. This is called Fisher information. This is very important statistics used in statistical literature. Okay. But here, the Jeffreys prior is defined based upon that. While we'll only consider like theta is just a scalar, but in general, if theta is a vector, this Fisher information becomes a matrix. Why? Because this second order derivative now is a Hessian, right? Theta is your random variable. For example, your likelihood is Gaussian, right? For example, it is some Gaussian distribution determined by mean and covariance, right? This can be your theta. Right? So if you choose this Gaussian likelihood as your likelihood, right? So if you want to calculate your facial information with respect to theta, you take the logarithm of your likelihood and take the second order derivative over the log likelihood, right, which is Hessian. Right? Now, remember, it is still a function with respect to x. X is a random variable. So we can take expectation, right? We take expectation with respect to this distribution. Here, it is Gaussian. And then it gives you the facial information. And facial information has a nice property is that it's always non-negative, right? If theta is vector, facial information is a positive semi-definite matrix. So this is the definition of the Jeffreys prior. So it sounds a little bit weird, but it actually acts as very nice properties. So again, we want to use a concrete example to showcase the Jeffreys prior. Right? So we use the binomial likelihood as an example. Suppose I run a binomial experiment with n trials, right? Remember, binomial distribution is actually n independent Bernoulli trials, right? So it is determined by the number of trials n and also the chance, the probability theta. Right? It's like using the coin tossing as an example again, right? Suppose you want to look at, you want to throw the coin for 100 times, you want to look at how many heads up in total, right? This is a typical binomial experiment. And the total number of heads up follows the binomial distribution, right? Parameterized by the number of coin tossing experiments and also the chance of each time you're gonna see the heads up. Right? So we know that the likelihood has this function. Right? We discussed about this before, right? This is just the probability for one particular realization, right? So you have observed that x heads up, right? If x takes 10, x is 10, right? So it is theta to the power of x, 1 minus theta to the n minus x, and then you need to multiply this combinatorial number, right? To count how many possible realizations give the same outcome in total. Right? So now let's construct a Jeffreys prior or theta. Right? According to the definition, we're gonna take a logarithm of likelihood, right? So it's just a pretty straightforward, right? And and of course, this part we like a combination number, right? Here we omitted because we're gonna take the second order derivative over the log likelihood. So you take the second derivative, you take the derivative over the log likelihood with respect to theta. This is just a constant to theta, so this, you can just throw it out, right? And you take it again. So this is your second order derivative of the log likelihood, right? So now we need to take this expectation of the second order derivative. Remember, the second order derivative is still a function of x, and x is a random variable. So you can take expectation with respect to x, right? So we know that the expectation of x is simply the number of trials times the probability theta. Right? This is a known result for the binomial distribution we discussed previously. How to conveniently get this this expectation, right? So now, if we take expectation of this guy and take minus sign, we see that the minus here will be canceled, right? So the expectation over x is n theta, n minus x is n minus n theta, right? It's by a trivial simplification, you get your information to be n over theta minus times 1 minus theta. Now you construct Jeffreys prior. Remember, Jeffreys prior is proportional to square root of the facial information, which is proportional to theta to the power of minus half, 1 minus theta to the power of minus half. Okay. This actually is a beta distribution. Remember, beta distribution in general has the form theta to the A1 minus theta to the B, right? This is beta distribution, right? And here is beta. Sorry, it's A minus 1 and B minus 1, right? So here A and B will be half and half. Right? B minus 1, right? So we can see that the Jeffrey prior over theta is a beta distribution parameterized by half and half. Right? So how does it compare with the uniform prior? Right? So again, we can think about that, right? To construct uninformed prior, right? We have different choices. Right? A more intuitive choice will be, okay, I'm gonna assign equal chance for theta to take different values. Right? Theta is between 0 and 1. Right? That corresponds to a uniform distribution, which is the right line here. Right? And the blue line here is our Jeffreys plot, which is beta half and half. And by the way, in this special case, right, because theta is a probability, right, between 0 and 1, it's probability, for example, you see the heads up when you toss a coin, right? So this uniform distribution is also can be viewed as a special instance of beta distribution with 1, 1 as a parameters. So you can see that the uniform distribution is a line, right? It's a horizontal line, right? And for the Jeffreys part is some a little bit weird blue line here, right? But what's the advantage? What's the benefit of the Jeffreys part? Right? Now we need to look at the likelihood itself. If we look at the binomial likelihood itself, we find that if the theta takes values around half, you see that no matter how x varies, how the observation varies, the likelihood value nearly doesn't change at all, right? If theta takes right half, right? So you can see this part is what? It's just half and half, right? It's half to the power of n, right? This has the likelihood value has nothing to do with the actual observation x, right? So of course, if you take some value approximately surrounding half, well, the data will take the least effect. Right? But when will data takes the most effect? It takes the strongest effect, or take the greatest effect when theta is at the two extremes, right? Either 0 or 1. That's the likelihood properties. Now, let us look at the Jeffreys part, the blue curve. You can see that the Jeffreys part is consistent with the data effect. When the theta value takes in the middle, right, half, it has the smallest stress, right? Has little stress on the density, right? Only when theta gets close or closer to the two extremes, it has the largest effect. So you can see the consistency between the prior and the likelihood.
At the start, you mentioned if the parameter release,
yeah,
then we can just one over
mm-hmm.
So here also it's bounded, right?
Mm-hmm.
So we can say the prior has to be proportional to 1 over.
Yeah, actually, it doesn't to be bounded because even it's not bounded. You can your Jeffreys prior is still defined in this way. So it's as I just mentioned, right? This is a improper prior. That means if theta is not bounded, if we do the integral, it will diverge. Right? It gives infinity. So actually, it's not a valid prior. It just wants to incorporate some knowledge or bias toward the distribution of the theta. As long as you can calculate value posterior of theta, that's fine. That's totally a pragmatic choice. Mhm.
Or if you have a boundary variable of parameters, you can have an uninformative type of this boundary parameters. So if you go to the maybe like so this is like 20 years.
Mhm.
So in this case, our parameter is not.
Yeah.
We already have an information.
Yeah.
So why are we doing this like that?
Okay. Uninformed T-par is not unique. You have a family of pairs which all can be called uninformed T-pars. You need to weigh and balance which uninformed T-par is more appropriate for application.
So we can use this one also.
Yeah, you can use this one. You can use that. We just compare the difference between these two types of uninformed T-pars. But there's I think there's a misleading in the name. I don't like those objective Bayesian guys to give such a name, uninformed T-pars. It doesn't mean uninformed T. Uninformed T does not mean no informed T. Actually, it's not possible for Bayesian people to give you a no informed T-par. So you're always trying to incorporate some induction bias or bias over the distribution. But for the objective Bayesian people, they want to minimize such kind of bias or preferences. Okay. So in our particular example here, I mean, both the uniform and the Jefferson pairs can be viewed as uninformed pairs, but then we need to look at their difference and which one do you prefer more. But here I want to highlight a better property of Jefferson pairs is that it aligns with the data likelihood more. Okay? So that you can imagine the posterior distribution will be more influenced by the likelihood. Right? If you use uniform distribution, you see that, okay, likelihood has the largest effect here, and least effect here. But for the uniform distribution, they have the same effect. So they're kind of contradictory in integrate them together to calculate posterior. Right? So that means Jefferson pair is more favorable in this case.
So this is a uninformative prior, right? So why are we imposing that this is a binomial?
Why do we imposing? We assume this is binomial distribution. So
uninformative, then we have no idea what distribution data is it. We have to start with a uniform distribution.
No. So so likelihood is talking about given the model parameters, how do you model the data? And uninformed T-par is about the model parameters. These are different. We're assuming, okay, we know the likelihood is binomial. But how do I construct prior over the parameters theta to be as little influence as possible on the posterior? So we always assume we know the likelihood.
I have a question about the philosophy behind the definition of Jefferson phi. Could you get back to the definition? I can understand that the Fisher information is somehow information by theta. But what is why you just didn't define the Jefferson prior to the proportion to I of theta, and that's the square root of that.
Well, because later we will show that if you define it this way, it is invariant to any translation. If you don't take square root, well, it doesn't have such a good property.
Is that an intuition behind this definition, or just that it is invariant?
Just to construct invariant. Well, I mean, for intuition, that means you might need to look at the feature information itself. It actually captures some underlying geometry, the geometry underlying the distribution. But some genius, maybe this guy, the inventors from Jeffrey, he found out, okay, this nice properties can be used to construct a translation invariant part.
So it's not like when we add so this possibility distribution can be used as a prior for the next set of experiments. We will keep on adding to the posterior, right? So and then like when we had like for better distribution A equal to 2 and B equal to 2, like so it was a function like this, and then it was slowly shrinking, and we would have a spike, right? And now we see it's a concave function like this. So how does that change when we start to add more data?
Okay, so that's another story. So here we assume, okay, you don't have too much data. And you don't have too much data, you still want your prior doesn't have much influence on the posterior. But on your story, for example, you have like infinite amount of data. Actually, as long as your prior is not weird, the prior doesn't take any effect. So there's a Bayesian version of law of large numbers. So it tells you that, for example, you have a flat prior, right? Flat prior, but and we know that when the amount of observed data is not large, you have some kind of a reasonable posterior, right? However, when the amount of data goes to infinity, so this posterior will converge to a spiky distribution. That means it just converges to a point. That's reasonable because with more and more data, your uncertainty about the parameters keeps reducing, right? And finally, you're 100% sure what the value it is. There's no more randomness on that. Right? So here, I mean, when we talk about uninformed prior, we're just talking about, okay, suppose I only have 10 observations, right? In that case, any kind of like strong biased prior will largely influence the posterior, right? In that case, how can we construct the prior to reduce such kind of influence as most as possible?
I think over time will also be.
Yeah. If you have a lot of data, well, you might not need to really care about the prior. Any other question regarding the philosophy? Usually, if you want to construct uninformed prior, you need to know the likelihood. Like suppose given some model parameters, how are you gonna model these observations? Otherwise, it's very hard to construct uninformed prior. But it's kind of likelihood dependent, as what he just mentioned. Okay. So now I want to briefly show how Jeffrey's prior activates the translation invariance property. Right? So let us consider general translation. Right? So this is a very useful property. I mean, not only used for improving the translation invariance for Jeffrey prior, you're gonna use these tricks from time to time. So let us consider a general translation phi, right? So you have some random variable theta. I want to construct a transform random variable phi by applying the transformation function h, right? So first, we directly construct Jeffrey prior over phi. Right? That means, according to the definition, the Jeffrey prior over phi will be proportional to this square root of the feature information with respect to phi. Right? So now we want to construct the connection of this prior form to theta. So to do this, we can use chain rule, right? Because the efficient information of phi, according to the definition, is the negative expectation of the second order derivative of the log likelihood with respect to phi. Right? So just apply the chain rule. That means you're going to first take the derivative with respect to theta and then times d theta over d phi, right? But you have to do this twice because it's second order derivative. Right? I will leave it as an exercise. But after some arrangement, you get this information, feature information in terms of phi can be written as expectation of this guy. So it actually contains two terms. First is the second order derivative of the log likelihood with respect to theta times the square of the derivative d theta over d phi plus the first order derivative of the log likelihood with respect to theta multiplying with the second order derivative of theta with respect to phi. And a key observation here is that if you take expectation, we know that we're going to take expectation over each term, right, and add them together. Right? So the key observation here is that the expectation of the second guy is simply 0. Some of you may have seen this result before, right? Just forgive me, I will give a quick explanation, right? I mean, so you take expectation of the first order derivative of the log likelihood with respect to theta is simply 0. Why? The reason is that as a value likelihood, right? Likelihood is actually a distribution, right? The integral of this density with respect to x will be 1, right? That means if you take the derivative on both sides of this equation, you get 0, right? And for the left-hand side, which is take the derivative of this integral with respect to theta, right? And assuming some nice properties on mild regularity, right? You can switch the integral and the derivative. That means you can first take the derivative of the density with respect to theta. That means the integrand, and then take the integral, right? So that means you take this guy, right? Now, let us multiply this to constant. This is just 1. Right? You multiply p x given theta divided by p x given theta. And then it ends with 1, right? It doesn't change the integrand at all, right? So, but here it gives a very important observation, because if you look at this term together, right? Let me, oops. If you look at these guys together, right, and leave this density away, right, outside, that means the terms inside this square bracket. You see that this is essentially the derivative of log likelihood with respect to theta. It's just apply the chain rule. You see that immediately. Right? So, and outside of this square bracket, it multiplies with the probability density of x given theta. Right? So that means this integral essentially is an expectation of the first order gradient or first order derivative of the log likelihood with respect to theta. This gives us the result, the expectation of this first order log likelihood. First order derivative of log likelihood simply 0. Right? So that means we can throw out this term. Okay? So this guy is simply 0, and we only leave this guy. Right? If we take expectation, we know that this guy is the feature information of theta. So you can see that your Jeffrey prior, no, your facial information of phi, your facial information with respect to phi is the facial information with respect to theta times the square of d theta over d phi. Because our Jeffrey's prior over phi is proportional to the square root of the facial information with respect to phi, right? So that means the Jeffrey prior over phi is actually proportional to this guy. Square root of facial information with respect to theta times the absolute value of d theta over d phi. Okay. That's this result. This result is derived from we directly construct the Jeffrey prior over phi, right? But we want to compute this this prior in terms of theta, we get this result. So now let us do this in another way. We just construct a Jeffrey prior over theta, meaning that I got a theta is proportional to this square root of facial information of theta. And then I define my phi as a transformation theta, meaning that it's just h of the theta. And then according to the prior of theta, we can use random variable transformation to get density about phi, right? If you just apply the formula we used before, okay, it will give the same form. Right? This actually shows that the Jeffrey's prior is a translation invariant. Okay. Meaning that, okay, I can construct a Jeffrey prior for any random variable theta, right, after any kind of variable transformation. Your density of the transform variable will also follow the Jeffrey's prior. That's the amazing property of the Jeffrey's priors. So that means, okay, when you apply Jeffrey's priors, you really don't need to worry about the form of the what kind of translation invariance expected in your likelihood. Right? As long as your likelihood shows some kind of translation invariance, the Jeffrey prior will automatically satisfy that translation invariance as well. Oh, here we assume H is bijection, meaning that you can directly use the transformation of a random variable to compute the probability densities. This is not like arbitrary, like for example, you reduce dimension. That's not allowed. Any question? Okay. So now, if we look at the Gaussian likelihood again, right? That's our concrete example. We always use Gaussian likelihood. If you construct Jeffrey prior over mu and the sigma square, right? You see that it is the Jeffrey prior about mu is proportional to constant, and the Jeffrey prior over sigma is proportional to 1 over sigma. I'll leave it as an exercise for you. You can see that they're actually unified in the Jeffrey's prior framework. So you can see that interesting point is that we don't need to really look at which kind of translation invariance this Gaussian likelihood satisfies. Although we have analyzed that, we know for mu it satisfies the shift invariance. For sigma, it satisfies the skew inverse. Right? So we construct the prior independently to satisfy those two types of invariance. However, if you apply Jeffrey prior directly over mu and sigma, it just gives us the same result. That means it's automatically satisfy all kinds of translation invariance expected in the likelihood. Okay, so although Jeffrey's prior are kind of like very elegant and powerful, it is usually not conjugate. If you choose Jeffrey priors over mu and the standard deviation for Gaussian likelihood, the posterior mu will be a student T distribution. If you're interested, you can take a look. You can try to derive that, right? And it works pretty well for single parameters, but for multi-dimensional parameters, the Jeffrey priors usually don't work very well. So it is not perfect, actually. So in theory, although in theory it has many nice properties, but for multi-dimensional parameters, it often exhibits poor convergence properties, not very reasonable estimates, and so on. Okay, and the last thing I want to talk about to the uninformed prior is a more general category. It's called reference priors. So the reference prior is formalized what exactly we mean by an uninformed prior. We want to find a prior function that can maximize the distance between the posterior and prior as data observation is made. So basically means I want to make the posterior to be as different as possible from the prior, so that the prior has little influence on that, right? If your prior has a strong influence, it should kind of like attract, appeal the posterior to make it as close as possible. But now, if I can find a prior function that makes their distance to be as far as possible, that means the data will take most effect in calculating posterior. Then there brings the problem, right? How we need to first give some measure of distance between the distributions, right? So a commonly used measurement is called KL divergence, as we discussed previously. But rigorously speaking, again, KL divergence is not a distance, because distance requires symmetric, right? But KL divergence is not symmetric. And usually, if we use KL divergence to construct a reference prior, we essentially obtain the prior by maximizing the expected KL divergence between the posterior and the prior. So this is the KL divergence, right? This T here is observation, of course, because observation itself is just random variable values. It has some randomness, so we need to take expectation on that. So if we can maximize this expected KL divergence to find theta, and this to find the P of theta, we call this prior as a reference prior. Okay, so those are about uninformed priors. Although in practice we don't have too much chance to use uninformed priors, but you should know the concepts with an idea. And also in some scenarios, the Jeffrey prior is pretty useful. Like if you want to do Bayesian sparse learning, you want to know the weights, you want to learn the weights of the features. You don't want to, and you don't know too much about the weight itself. You can assign Jeffrey prior over the weights. That's a common choice. Yeah, you can use that. This is called this. I forgot. This is another. This has your symmetric version. The symmetric revision is has a special name. It is divergent. But for computational convenience, people usually use this. Yeah, you can definitely use this, like P to Q from Q to P, right? And you can take half, right? So there's a special name of this. A special name. You can use that for sure. But you see that the computation difficulties when you switch the order will change differently. So people will, it's funny that in Bayesian inference, you often found that if it is easy to compute this, then it's very hard to compute this. If it's easy to compute this, it's very hard to compute this. That's why people rarely use this modified version. Okay, so a third important topic or concept is called exchangeability and the definite theory. So definite theory will justify the rationale of Bayesian model. Why it's reasonable for us to assume there's a prior distribution over the latent random variable or model parameter theory. So definite theory gives you a perfect theoretical justification. Okay, so again, when we talk about the difference between Bayesian and frequentist, we consider a general likelihood or distribution P of X given theta governed by some model parameter theta, right? For the frequentist point of view, I believe theta is an objective constant, right? I need to estimate from IID samples from X1 to Xn, right? And for Bayesian, we believe theta is some latent random variable. It was also sampled from some prior distribution, right? And then given theta, we sampled observation X1 to Xn. So although it sounds kind of like a philosophical choice, right? So the question is, can we justify Bayesian model with some mathematical evidence? Right? If we can show that for particular type of data, this data, the generation of this data is indeed corresponding to such a Bayesian sampling procedure, then we get the theoretical support of our Bayesian model. Right? So to talk about that theoretical support, we need to know the concept called exchangeability. So exchangeability is a very, very important modeling choice in Bayesian work. So it is much more flexible than IID assumption, but it also gives you a certain simplification. Right? So we know that most of the statistical analyses are based on IID observation X1 to Xn. That means we assume X1 to Xn are totally independent, so their joint probability is the product of their individual probabilities. Right? Although this assumption is convenient, it may not be reasonable in many problems, like weather conditions. Right? You can't assume today's temperature is independent from tomorrow's temperature, right? And is independent to the temperature the day after tomorrow, right? That's not possible, right? For stock price, you cannot assume, okay, yesterday's stock price has nothing to do with today's stock price. So actually, the random variables are often strongly correlated to each other. Right? In such kind of cases, how can we model them, right? So exchangeability will give you a much weaker assumption. It can account for those strong dependencies between the random variables, while still give you some kind of nice properties for computation. Right? So what is exchangeability? Like, we first talk about finite exchangeability. So suppose we have n random variables and an arbitrary permutation, pi 1 to pi n just means, suppose this is 1, 2, 3, right? One permutation could be 3 to 1, right? Another permutation could be 2, 1, 3, whatever. So this is just this pi just map the index after the permutation, right? So we denote this n random variables is exchangeable in distribution. It just means the probability or probability density that those n random variables takes the value of any permutation from the sequence x1 to xn is the same. So here is one concrete example, right? Although stating this definition is kind of like weird, but the example is very simple. Like suppose we have values x1, x2, x3. Right? There we can take a sequence value 1, 2, 3. Right? So if we say the three random variables x1, x2, and x3 are exchangeable, just means the probability that x1 takes 1, x2 takes 2, x3 takes 3 is the same as you take x1, x2, x3 as the random any permutation of these three values, like the same as 2, 3, 1, or x1 is the same as probability x1 equals to 3, x2 is 1, x3 equals to 2. Right? As long as those values are just the permutations, it doesn't change the joint probability. That is called exchangeability. Any question? Okay. So now we can extend this definition to the infinite sequence. So suppose we have an infinite sequence of random variables, xi, right? So x1, x2, x3, x5, you can count to infinity, right? So we call this infinite sequence of random variable is exchangeable if for any finite set of random variables in this sequence, they are exchangeable. This is called exchangeability in infinite sequences. So this definition is very important in theory, but you only need to know the definition. We won't use that to do any proof, right? So so the exchangeability essentially assumes some symmetry of the density, meaning that okay, your n random variables, right, takes these values x1 to xn. You can do arbitrary permutation over those values, and then the probability density takes the same set of values, won't change. This is essentially a symmetry, and it also tells you that the IID assumption is a special type of exchangeability, right? But not vice versa. It is exchangeable, doesn't mean it's IID. Right? Right? IID must give you the exchangeability, right? Because the probability density of IID when the variables will simply be the product of their individual probabilities, right? So you can do arbitrary permutation, it doesn't change. Right? However, when it is exchangeable, it doesn't mean you can decompose this joint density as the product of their marginal densities, right? So here we give one more concrete example, right? This is a very well-known example. It's called poly-urn. So suppose you are given an urn with B0 black and W0 white balls, right? So you use the following procedure to draw the balls, right? So every time you draw a ball at a random from the urn, and just note its color, right? If the ball is black, then your outcome is 1. Otherwise, your outcome is 0. Right? And then in whichever case, you're going to place 8 balls of the same color in the urn. Right? You just repeat this procedure. So suppose we do this urn sampling, this ball sampling procedure for 4 times. We consider 2 possible outcomes for the 4 samples, right? 1, 1, 0, 1, 1, 0, 1, 1. So that means the outcome for the first sampling is 1. That means black ball, white ball, black ball, right? And the second probability is about first is black ball, and then white ball, then black ball, black ball. So you can see that the value of these outcomes are for the 4 random variables, right, are the same set. They're 1, 1, 0, 1, right? They're just a permutation. Right? In the first case, we have x1 takes 1, x2 takes 1, x3 0, x4 1. Right? In the second case, you have x1 takes 1, x2 takes 0, x3 takes 1, x4 take 1. Right? It's just a permutation of the values those 4 random variables can take. So first of all, do you think these 4 random variables are independent? Why? Why is not independent? Yes, exactly, right? If you look at the sampling procedure, right, whether each time you're going to place 8 balls of the same color, your example, right, it really depends on the outcome of the current sample, right? If you get black ball, you're gonna place A black balls. Right? If you pick white balls, you're gonna place A white balls. Of course, it's gonna affect the chance you pick up the next ball. Right? So obviously they're not independent, right? But if you calculate their joint probability when taking these different values, right, they will be exactly the same. Okay. I will leave it as I will leave it as an exercise for you guys. It's kind of like a entry level of statistics. Right? So now we're well prepared to say defining theory. So what's the defining theory? Suppose we have a binary sequence. Well, it's infinite sequences, meaning that each xi is a binary variable. And this variable is exchangeable. It is exchangeable. We know the definition of exchangeable infinite sequences just means any finite subset of this sequence is exchangeable. Right? Then we can tell that they are exchangeable if and only if there exists a distribution function f on 0 to 1 such that for any finite number n, the joint probability of the corresponding, the first n variables in the sequence is this integral. Right? So, of course, the joint probability just means that, okay, the first random variable x takes this value, x1, second takes x2 until the nth random variable xn takes xn, right? So all those values are either 1 or 0. And Tn is actually the summation of all the outcomes. So it's actually a number of ones. Right? So this guy actually is a probability density or theta, because this is a distribution function. That just means it's cumulative distribution function on 0, 1. So you take derivative, it simply means a probability density of theta. Okay? So this integral actually tells us this is an integral, actually tells us theta here is a latent random variable theta. And it has a prior distribution P of theta, which is determined by F. Okay. And what is about F? F actually is a distribution of this limiting frequency. So if you average first n random variables in your sequence, it is still a random variable, right? Because just the average of set random is still a random variable. No, because we have an infinite sequence. Right? If you take a limit of this average, it's still a random variable. And the distribution over this limit average is F. And the integral here, right? This part, the power regarding theta and 1 minus theta, right? So you can view them as essentially a Bernoulli distribution, right? Conditional on particular choice of theta. So now it's pretty clear that this integral acts a hierarchical sampling procedure, right? So you first sample the value of theta according to F or according to the density P. It's the same thing. And then given theta, you use Bernoulli distribution to sample each observation of x1 to xn. Then you get this marginal joint probability over x1 to xn with theta marginalized out. That's what definite theory tells us. In other words, definite theorem exposes the fact that there is an underlying sampling procedure to generate infinite exchangeable binary sequence. Okay. So you got some theta sampled from P of theta, which is actually the cumulative distribution of the average limit. And then given theta, you sample each value of x1, x2 to any variable in your sequence conditionally independently. And if you just calculate the marginal distribution of x1, x2 to any xn, it will give you this interval. That's the inside of a definitive theory. And that's why it justifies the Bayesian model, because it tells you, okay, it indeed contains a sampling procedure on theta, because you indeed have some prior distribution over theta. Okay, we're gonna give a little bit more discussion about definitive theory on Thursday. And then we'll start with our Bayesian models. We'll start with generalized linear model with the nonlinear feature mappings.